A multi-wire branch circuit involves sharing a neutral conductor between two hot conductors originating from different poles of a two-pole breaker. According to the National Electrical Code, two circuits can indeed be tied to a two-pole breaker, creating what's known as a multi-wire branch circuit. This configuration has specific requirements that must be met to ensure safety and code compliance. Firstly, the two circuits must be connected to opposite poles of the two-pole breaker. This ensures that the voltage between the two hot conductors is higher than the voltage from either hot conductor to neutral, usually 240 volts in a 120/240 volt system. Secondly, the neutral conductor must be common to both circuits. This shared neutral carries only the unbalanced current between the two hot conductors, potentially reducing the overall current in the neutral wire. Thirdly, the circuits must be clearly identified using white and black wires or other contrasting colors to differentiate between the hot and neutral conductors. This color coding helps prevent accidental short circuits and ensures proper wiring during maintenance or repairs. The circuits must be connected to the same phase. This is inherent when using a two-pole breaker, as both poles are derived from the same phase of the electrical supply. There are several advantages to using multi-wire branch circuits. Firstly, it saves space in the electrical panel. While sharing a neutral conductor, the number of wires and terminations within the panel is reduced, freeing up valuable space for other circuits or equipment. Secondly, it simplifies wiring. Running a single neutral conductor instead of two separate neutrals can reduce the amount of wiring needed, making installations faster and easier. Thirdly, it provides redundant protection if one circuit trips. If one of the circuits experiences an overload or short circuit, the two-pole breaker will trip, interrupting power to both circuits and preventing potential damage or hazard. Now, addressing the question of using individual single-pole breakers as a double pole by mechanically connecting their handles with a tie, the National Electrical Code does not approve this practice. This is because the tie may not reliably ensure that both breakers trip simultaneously under fault conditions. If one breaker trips due to an overload or short circuit on its associated circuit, the other breaker may not trip, leaving the other circuit energized and potentially creating a safety hazard. The purpose of a two-pole breaker or a common trip breaker is to disconnect all ungrounded conductors of the circuit simultaneously. This is especially important when dealing with 240-volt appliances or equipment, as energizing only one leg of the circuit can damage the appliance or create a shock hazard. Approved methods for providing double pole protection include, firstly, using a listed two-pole breaker. This is the most straightforward and reliable way to ensure that both conductors of a 240-volt circuit are disconnected simultaneously. Two-pole breakers are designed and tested to trip together under fault conditions, providing reliable protection. Secondly, using two single-pole breakers mechanically interlocked with a common trip handle. These devices are specifically designed to ensure that both breakers trip simultaneously when one experiences an overload or short circuit. The common trip handle provides a positive mechanical link between the two breakers, ensuring that they operate together. When installing or modifying electrical circuits, it is essential to consult the National Electrical Code and local electrical codes. These codes provide detailed requirements and guidelines for safe and compliant wiring practices. It is also recommended to hire a qualified electrician to perform any electrical work, as they have the knowledge and experience to ensure that the work is done safely and correctly. It's crucial to understand the ampacity of conductors used in branch circuits. Ampacity refers to the maximum current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code, specifically Table 310.15b16, provides ampacity ratings for various types of insulated conductors based on their size, insulation type, and ambient temperature. For example, a 14 American wire gauge copper conductor with type THHN insulation, commonly used in residential wiring, typically has an ampacity of 15 amps when used in a circuit with no more than 3 current-carrying conductors in a raceway or cable. A 12 American wire gauge copper conductor with the same insulation type usually has an ampacity of 20 amps under similar conditions, and a 10 American wire gauge copper conductor is generally rated for 30 amps. These ampacity ratings are based on specific conditions, and directing factors must be applied when the conductors are exposed to higher ambient temperatures or when more than 3 current carrying conductors are bundled together in a raceway or cable. Directing factors are outlined in NEC Table 310.15 cone. For example, if a cable contains more than 3 current carrying conductors, the ampacity of each conductor must be reduced to account for the increased heat generated by the additional conductors. Similarly, if the conductors are installed in an area with a high ambient temperature, their ampacity must be reduced to prevent overheating. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. These devices must be selected with an ampacity rating that matches the ampacity of the conductors they protect. For example, a 14 American wire gauge conductor with an ampacity of 15 amps should be protected by a 15 amp circuit breaker or fuse. It's crucial to avoid oversizing the overcurrent protection device, as this can allow the conductor to overheat and potentially cause a fire. The National Electrical Code, specifically Section 240.4d, provides rules for overcurrent protection of conductors. This section states that conductors must be protected against overcurrent in accordance with their ampacities, with some exceptions for specific types of equipment and applications. One common exception is the next size up rule, which allows the use of a slightly larger overcurrent protection device if the conductor's ampacity does not match a standard breaker or fuse size. However, this rule is subject to certain limitations and should be applied carefully to avoid exceeding the conductor's safe operating temperature. Voltage drop is another important consideration in branch circuit design. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance and the current flowing through it. Excessive voltage drop can cause problems with equipment performance, such as dimming lights, reduced motor torque, and malfunctioning electronic devices. The National Electrical Code recommends limiting voltage drop in branch circuits to no more than 3% at the furthest outlet for lighting, heating, and power loads, or 5% for feeder circuits plus branch circuits. To minimize voltage drop, it's important to use conductors with adequate size and to keep circuit length as short as possible. The voltage drop can be calculated using Ohm's law and the conductor's resistance per unit length. Online voltage drop calculators and software tools are also available to simplify the calculation process. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, preventing voltage differences that could create a shock hazard. The National Electrical Code, specifically Article 250, provides detailed requirements for grounding and bonding. This article covers topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal enclosures and raceways. A grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes, that are connected to the building's electrical system. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current to dissipate. Equipment grounding conductors are used to connect the metal parts of electrical equipment, such as appliances, fixtures, and enclosures, to the grounding electrode system. These conductors provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the equipment in the event of a fault. Bonding is the process of electrically connecting all metal parts of the electrical system together, including metal enclosures, raceways, and equipment frames. This ensures that there are no voltage differences between these parts, which could create a shock hazard. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire or metal straps that connect the metal parts together. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electrical shock. A GFCI monitors the current flowing in the hot and neutral conductors of a circuit and trips if it detects a difference of 5 mA or more. This difference indicates that current is leaking to ground, which could be due to a person touching a live wire or a faulty appliance. The National Electrical Code requires GFCIs in certain locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. GFCIs are typically installed in receptacles or circuit breakers and provide protection for all outlets downstream of the device. Arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arcing faults. An arcing fault is an unintentional electrical discharge that can occur when a wire is damaged, loose, or corroded. Arcing faults can generate intense heat and ignite nearby combustible materials, leading to a fire. The National Electrical Code requires RFCIs in certain locations to protect against arcing faults. RFCIs are typically installed in circuit breakers and provide protection for the entire branch circuit. There are two types of RFCIs: branch/feeder RFCIs and outlet branch circuit RFCIs. Branch/feeder RFCIs protect the entire branch circuit, while outlet branch circuit RFCIs protect only the outlets downstream of the device. When working with electrical circuits, it's important to follow lockout/tagout procedures to prevent accidental energization. Lockout/tagout involves disconnecting the power to the circuit and installing a lock and tag on the disconnect switch to prevent it from being turned on. This ensures that the circuit remains energized while work is being performed, preventing electrical shock or injury. Before starting any electrical work, it's important to verify that the circuit is de-energized using a voltage tester. A voltage tester is a handheld device that can detect the presence of voltage in a circuit. By testing the circuit before starting work, you can ensure that it is safe to proceed. The National Electrical Code requires that all electrical work be performed by qualified individuals who have the knowledge and experience to do the work safely and correctly. Qualified individuals typically include licensed electricians, electrical engineers, and other trained professionals. When hiring an electrician, it's important to verify that they are licensed and insured. A licensed electrician has met the requirements of the state or local licensing board and has demonstrated their competency in electrical work. Insurance protects you from liability in case of accidents or damage caused by the electrician's work. Electrical permits are required for many types of electrical work. A permit is a document that authorizes you to perform electrical work and ensures that the work is inspected by a qualified inspector. Electrical permits are typically required for new installations, additions, and alterations to electrical systems. To obtain a permit, you must submit an application to the local building department and provide detailed information about the proposed work. After the work is completed, an inspector will visit the site to ensure that the work meets the requirements of the electrical code. Electrical inspections are performed to ensure that electrical work is done safely and correctly. An electrical inspector is a qualified individual who is trained to identify potential hazards and code violations. During an inspection, the inspector will examine the wiring, equipment, and grounding system to ensure that they meet the requirements of the electrical code. If the inspector finds any violations, they will issue a correction notice that must be corrected before the work can be approved. In addition to the National Electrical Code, many states and local jurisdictions have their own electrical codes. These codes may be more stringent than the NEC and may include additional requirements. It's important to be familiar with the electrical codes that apply to your area before starting any electrical work. The National Electrical Code is updated every 3 years. The latest edition of the NEC is available from the National Fire Protection Association. It is important to stay up to date on the latest changes to the NEC to ensure that your electrical work is code compliant. Changes to the NEC can affect many aspects of electrical installations, including wiring methods, grounding requirements, and overcurrent protection. In addition to the NEC, there are many other resources available to help you with electrical work. These resources include textbooks, online courses, and training programs. It's important to take advantage of these resources to improve your knowledge and skills. By following safe work practices and adhering to the electrical code, you can ensure that your electrical work is done safely and correctly. Electrical safety is everyone's responsibility. By taking the necessary precautions, you can protect yourself and others from electrical shock, fire, and other hazards. Remember to always turn off the power before working on electrical circuits. Use the proper tools and equipment, and follow lockout/take-out procedures. If you're not comfortable working with electricity, it's best to hire a qualified electrician to do the work for you. Electricity is a powerful force that can be dangerous if not handled properly. By taking the necessary precautions, you can stay safe and prevent accidents. Regular maintenance of electrical systems is essential for ensuring their safe and reliable operation. Maintenance tasks include inspecting wiring and equipment for damage, tightening connections, and testing ground fault circuit interrupters. It's also important to keep electrical panels and equipment clean and free of obstructions. Regular maintenance can help to prevent electrical problems before they occur. Troubleshooting electrical problems requires a systematic approach. Start by identifying the symptoms of the problem, and then use a process of elimination to narrow down the possible causes. Use a voltage tester and other diagnostic tools to test circuits and components. Be sure to follow safe work practices and disconnect the power before working on any electrical circuits. When making electrical repairs, it's important to use the proper materials and equipment. Use conductors with the correct ampacity rating and insulation type. Use approved connectors and fittings. And be sure to follow the manufacturer's instructions for all equipment. Electrical modifications should be carefully planned and executed. Before making any modifications, be sure to obtain the necessary permits and approvals. Follow the electrical code and use qualified personnel. It's also important to document any modifications that are made to the electrical system. Energy efficiency is an important consideration in electrical design. Use energy-efficient lighting in appliances. Install occupancy sensors and timers to control lighting and equipment. And consider using renewable energy sources, such as solar panels. By improving energy efficiency, you can reduce your energy consumption and save money on your utility bills. Smart home technology can be used to control and automate electrical systems. Smart home devices can be used to control lighting, appliances, and security systems. These devices can be controlled remotely using a smartphone or tablet. Smart home technology can improve energy efficiency, security, and convenience. Electrical safety for children is an important concern. Teach children about the dangers of electricity and keep them away from electrical outlets and equipment. Install tamper-resistant receptacles to prevent children from inserting objects into outlets, and supervise children when they are using electrical appliances. Electrical safety in the workplace is essential for preventing accidents and injuries. Provide employees with training on electrical safety. Use safe work practices and procedures, and ensure that all electrical equipment is properly maintained. Electrical safety audits can be used to identify potential hazards and code violations in electrical systems. An electrical safety audit is a comprehensive review of the electrical system that is conducted by a qualified professional. The audit will identify any areas where the system does not meet the requirements of the electrical code or where there are potential safety hazards. The audit report will provide recommendations for correcting any deficiencies that are found. And lastly, it is important to remember to call before you dig. Before digging, call 811 to have underground utilities located. This will help you avoid damaging underground cables and pipelines, which could cause injury or property damage. Calling 811 is free and can save you from costly repairs and potential hazards.